Deep in the heart of our galaxy, 26,000 light-years from Earth, something impossible is happening. The supermassive black hole at the center of the Milky Way, Sagittarius A star, is behaving in ways that challenge everything we thought we knew about these cosmic monsters. Imagine a black hole 4 million times the mass of our Sun, spinning at nearly the maximum speed allowed by the laws of physics, yet erupting in chaotic bursts of energy that follow no predictable pattern, blazing with flares that last from mere seconds to months at a time, while surrounded by young stars arranged in formations that shouldn't exist. Recent discoveries from the James Webb Space Telescope and cutting-edge artificial intelligence analysis have revealed that our galaxy's central black hole is not just active, but utterly unpredictable, constantly bubbling with mysterious activity that has astronomers questioning fundamental theories about how black holes behave. The first clue that something extraordinary was happening came in April 2024, when the James Webb Space Telescope captured something never seen before, a mid-infrared flare erupting from Sagittarius A star, followed by a corresponding radio flare that provided the missing piece of a decades-old puzzle about the black hole's behavior. For over 20 years, astronomers had observed flares in radio and near-infrared wavelengths, but the connection between these eruptions remained unclear until Webb's unprecedented observations revealed the complete electromagnetic signature of these mysterious outbursts. This discovery marked the beginning of a year-long campaign that would fundamentally change our understanding of what was thought to be a relatively quiet supermassive black hole. Using Webb's near-infrared camera to observe Sagittarius A star for a total of 48 hours across multiple sessions throughout 2023 and 2024, astronomers witnessed something that defied all expectations. The black hole was in a constant state of activity, with no periods of rest whatsoever. The observations revealed an ongoing cosmic fireworks display of various brightnesses and durations, with some flares appearing as faint flickers lasting mere seconds, while others blazed as blindingly bright eruptions that could be sustained for days. Even more intriguingly, the team discovered fainter variations that surged for months at a time, creating a spectrum of activity occurring over timescales ranging from brief moments to extended periods that challenge our understanding of accretion disk physics. What makes these observations truly remarkable is that Sagittarius A star never showed the same face twice. Every time astronomers pointed Webb toward the galactic center, they encountered a completely different activity profile, with the black hole presenting new and exciting patterns of behavior that appeared entirely random and unpredictable. Lead researcher Farhad Yousefzadeh from Northwestern University described the phenomenon as constantly changing, bubbling brightness that would suddenly explode into massive bursts before calming down again, with no discernible pattern governing the eruptions. This chaotic behavior sets Sagittarius A star apart from other supermassive black holes, which typically show more predictable cycles of activity and quiescence. The physical mechanism driving these enigmatic flares appears to involve two distinct processes occurring in the extreme environment surrounding the black hole's event horizon. The smaller, shorter-lived flickers likely result from turbulent fluctuations within the accretion disk that compress the swirling plasma, creating temporary bursts of radiation similar to solar flares, but occurring under conditions millions of times more extreme than anything in our solar system. These microflares emerge from the innermost edge of the accretion disk, just outside the event horizon, where gravitational forces are so intense that matter spirals toward the black hole at significant fractions of the speed of light. The larger, more dramatic eruptions appear to be powered by magnetic reconnection events, a phenomenon that occurs when two distinct magnetic field lines collide and explosively reconfigure themselves, releasing tremendous amounts of energy in the form of particles accelerated to nearly the speed of light. These magnetic reconnection events resemble cosmic versions of the static electricity sparks we experience on Earth, but operating under conditions so extreme that they can tap into the magnetic energy stored in the black hole's magnetosphere, creating brilliant flares that outshine entire star systems for brief periods. Recent computer simulations have shown that these reconnection events can produce hard, power law distributions of particles that create both synchrotron radiation, extending up to tens of mega-electron volts, and inverse Compton emissions, reaching into the tera-electron volt range. Perhaps the most startling revelation came from artificial intelligence analysis of Event Horizon Telescope data, which revealed that Sagittarius A star is spinning at an almost unimaginable rate, between 80 and 90% of its theoretical maximum speed. This discovery emerged from a groundbreaking study that used neural networks trained on millions of black hole simulations to decode the complex patterns hidden within observational data. The AI analysis required over 12 million computing jobs using distributed computing systems, creating a vast library of simulated black holes that allowed researchers to identify the precise characteristics of our galaxy's central monster. The implications of this extreme rotation rate are profound and unsettling. At such velocities, the black hole's spin is dragging space-time itself into a swirling vortex around the event horizon, creating frame-dragging effects so severe that they warp the very fabric of reality. Even more remarkably, the AI revealed that one of Sagittarius A star's rotation poles is pointed almost directly toward Earth, allowing us to peer down into the cosmic maelstrom and observe the glow of extremely hot electrons spiraling in the magnetosphere near the black hole's pole. This orientation explains why we can observe such dramatic flaring activity, as we're looking directly into one of the most energetic regions around the black hole. The high spin rate also suggests a violent and turbulent past for our galaxy's central black hole. Theoretical models indicate that such extreme rotation could only be achieved through a major merger with another massive black hole, an event that would have fundamentally altered the spin axis and angular momentum of the resulting object. Evidence supporting this scenario comes from recent observations, suggesting that Sagittarius A star may have awakened approximately 200 years ago, devouring cosmic debris in a feeding frenzy that briefly illuminated the galactic center before returning to its current state of chaotic activity. Adding to the mystery, the AI analysis revealed that the magnetic fields surrounding Sagittarius A star behave in ways that contradict existing theoretical models, indicating that our understanding of black hole magnetospheres requires significant revision. The deviation from established theory is so pronounced that researchers describe it as potentially defying prevailing models of how magnetic fields should behave in the extreme gravitational environment near a spinning black hole. This suggests that the complex interplay between rotation, magnetism, and accretion around supermassive black holes involves physics that we haven't yet fully comprehended. The Webb telescope observations also revealed subtle but crucial details about the physics of these flares through simultaneous observations at multiple wavelengths. When astronomers compared the brightness changes at 2.1 and 4.8 microns, they discovered that flares dimmed faster at shorter wavelengths than at longer ones, with time delays ranging from a few seconds to 40 seconds. This wavelength-dependent behavior provides direct evidence that particles in the flares are losing energy as they spiral around magnetic field lines, with higher energy particles radiating away their energy more quickly than lower energy ones. Such detailed observations of particle physics in the immediate vicinity of a black hole's event horizon were impossible just a few years ago. Recent discoveries have also revealed that the region around Sagittarius A star harbors unexpected populations of young stars, arranged in patterns that challenge our understanding of stellar formation in extreme gravitational environments. High-resolution observations have identified young stellar objects in the immediate vicinity of the black hole that describe similar orbits to already known evolved stars, and appear to be arranged in particular formations around the supermassive black hole. These discoveries suggest that star formation can occur even in the hostile environment near a supermassive black hole, with some young stars following clockwise orbital patterns that indicate they may have formed from a warped disk of material. Analysis of stellar populations in the galactic center has revealed evidence of inside-out galaxy formation, with the oldest stars concentrated in the innermost regions and younger populations distributed toward the outer edges. Surprisingly, researchers have detected an excess of young stars in the Sagittarius B1 region, representing several 100,000 solar masses of stars that formed approximately 10 million years ago. However, the two known young clusters in the galactic center account for less than 10% of the expected young stellar mass, suggesting that most star formation in this region occurs in loose associations that subsequently disperse, rather than in the massive, bound clusters typically observed in other galactic environments. Perhaps most intriguingly, astronomers have finally detected the long-predicted stellar wind from Sagittarius A star, a flow of gas that theory suggested should be blowing outward from the black hole, but had remained observationally elusive for decades. This missing wind represents another piece of the puzzle surrounding the black hole's unusual behavior, as its detection provides new insights into how matter behaves in the immediate vicinity of the event horizon, and how energy and momentum are transported away from the accreting system. The chaotic nature of Sagittarius A's flaring activity has led astronomers to propose continuous monitoring campaigns to determine whether these eruptions follow any hidden periodicities, or if they are truly random phenomena. Plans are underway to observe the black hole continuously for 24-hour periods using the Webb telescope, which would reduce observational noise and potentially reveal subtle patterns or structures in the flaring behavior that shorter observations might miss. Such extended monitoring could also help determine the relationship between the black hole's extreme spin rate and its unpredictable flaring activity. The discovery that magnetic reconnection events near Sagittarius A star can produce particles with energies extending into the TeV range has profound implications for our understanding of cosmic ray acceleration and high-energy astrophysics. Computer simulations suggest that the reconnection process can create multiple scales of magnetic structures, from tiny current sheets to macroscopic plasmoids several times larger than the black hole's Schwarzschild radius. These plasmoids can merge, grow to substantial sizes, and either be advected along the jet's sheath or fall back into the accretion disk, contributing to the complex energy transport mechanisms operating in the black hole's magnetosphere. The realization that our galaxy's central black hole operates in a state of perpetual chaos rather than following predictable cycles has implications that extend far beyond our own cosmic neighborhood. If Sagittarius A star, which is considered relatively quiet compared to active galactic nuclei in other galaxies, displays such complex and unpredictable behavior, it raises fundamental questions about how we understand supermassive black holes throughout the universe. The constant activity and extreme spin rate suggest that even dormant supermassive black holes may be far more dynamic and energetic than previously believed. Recent theoretical work on magnetic reconnection in black hole magnetospheres has revealed that the process can efficiently convert magnetic energy into kinetic energy of particles, with reconnection rates reaching several % of the speed of light. These rates are consistent with observations of flare timescales from Sagittarius A star, suggesting that magnetic reconnection provides a viable mechanism for powering the observed outbursts. The reconnection process also naturally explains the broad-spectrum emission observed from radio wavelengths through TeV gamma rays, as different populations of accelerated particles radiate at different characteristic frequencies. As we continue to observe Sagittarius A star with increasingly sophisticated instruments and analytical techniques, each discovery reveals new layers of complexity in the behavior of our galaxy's central black hole. The combination of extreme rotation, chaotic magnetic fields, unpredictable flaring activity, and unusual stellar populations creates a picture of the galactic center as one of the most dynamic and mysterious regions in the observable universe. The black hole's refusal to conform to theoretical expectations challenges us to develop new models of accretion physics, magnetohydrodynamics, and general relativity that can account for the full complexity of these extreme environments. The story of Sagittarius A's strange behavior represents a profound shift in our understanding of supermassive black holes, revealing them not as the relatively static, predictable objects we once imagined, but as chaotic, ever-changing engines of cosmic activity that operate according to physical principles we are only beginning to comprehend. As we stand at the threshold of even more advanced observations, with next-generation telescopes and AI-powered analysis techniques, we can expect that our galaxy's central black hole will continue to surprise us, challenging our theories and expanding our understanding of the most extreme objects in the universe. The mystery of why Sagittarius A star behaves so strangely may ultimately lead us to new discoveries about the fundamental nature of gravity, magnetism, and matter under conditions that push the very limits of physical law.